there anything peculiar that can happen for functions that are maybe L2 but still have discontinuities? Okay, and one of the common examples that you might come across when you have jump discontinuous functions are Gibb's phenomena. Okay, and the idea here is that jump discontinuities generate an overshoot, okay, in Fourier series, right? So maybe you've seen this before, right? Let's say you have the sine function, SIGN, not SINE, and you're trying to fit it with Fourier series, right? But you do it incompletely. Then what you're going to have is these oscillations as you near the discontinuity, right? Here and here, okay? And these are your Gibb's phenomena, okay? You still have a Fourier series that's a smooth function if it's truncated, right? You still also have what's called pointwise and L2 convergence, right? But you do not have uniform convergence. And so this is a nice way to disambiguate pointwise and uniform convergence, okay? So the idea with Gibb's phenomena is that you have these high amplitude oscillations, okay, that do not go away as n goes to infinity, right, as the number of terms you have go to infinity. And here, the example that we have, right, is f of x equals 1, minus 1, and 0. Let's say for x is in 0 to pi, x is in minus pi to 0, and 0 at x equals 0. Okay? And so if we essentially make a 2 pi periodic extension, okay, then we'll take f to be odd, right? Then f of x, right, can be approximated by this Fourier series, Bn sine of nx, right? Because this is an odd function, right? We're extending it 2 pi periodic, okay? What we can do is that we can show that these coefficients Bn are equal to 2 over n pi, 1 minus 1 to the n, essentially by compute, right, that Bn is equal to 1 over 2 pi integral from minus pi to pi sine nx f of x dx, right, which is going to be equal to 1 over pi integral from 0 to pi sine nx, okay, dx, okay? So this means that f of x is equal to 4 over pi, the sum for all n odd, all positive odd numbers, 1 over n sine of nx, okay? And so if I define big S n of x to be 4 over pi n odd all the way up to big N, 1 over n, okay, sine of nx, okay, this has a max at xn is equal to pi over n plus a half, okay? And we can also note that the limit as x goes to 0 from above, the limit as n goes to infinity of Sn of x is equal to 1, which is not equal to 0, okay? Which is actually equal to the limit as n goes to infinity, limit as x goes to 0 from above of Sn of x. So depending on how we take our limits, right, we get a different value for the right-hand limit of Sn of x. Moreover, right, Sn of xn, which would be where our max is, right, is, we can show that this is approximately equal to 1.18, okay, as n goes to infinity, okay? So Sn of x minus f of x's infinity norm is greater than 0 as n goes to infinity, okay? So essentially this peak here, right, it doesn't go away. It just gets smushed further and further basically into x equals 0 here, but it's still a peak above 0, okay? And so the condition that you need for uniform convergence is not there, okay? So you do not get uniform convergence, okay? But you do get pointwise and L2 convergence in this case, okay? So that's a peculiar situation that you might come across, okay? As long as you take enough terms, right, this issue is only going to come into play right here, right? But it's something to be aware of for applying, spectral methods to solutions with discontinuity, like shock solutions or something like that. So if you're trying to use Fourier series or something like that to solve an implicit Burger's equation, and you actually have a shock, then you're going to have to deal with these Gibbs phenomena that preclude uniform convergence. Okay. All right. So that's